And then I set this equation equal to 0. And because we know x is equal to y, I substituted in x for the y variable here in order so that we could find out basically what x is equal to. So I get 24y squared minus 24x is equal to 24x squared minus 24x. In this situation, I took out 24x, so I got 24x times x minus 1, which gives us x is equal to 0 and x is equal to 1. So our critical points are 0, 0, since we have x is equal to 0, and then x is equal to y, so that means y is also 0. And then 1, comma 1, same situation, x is equal to 1, y is equal to x, so it's 1 again. So the second step was we need to classify each of our points, basically. So I did that by doing d is equal to fxx dot fyy minus fxy all squared at each point. So fxx is equal to 24x minus 24y. And then when I take the partial derivative of x again, 24x is just 24, and then y is a constant here, so negative 24, 1 is just 0. I mean, y is just 0. F of y, I get 24y squared minus 24x. 24y squared is 48y when we take the partial derivative with respect to y. Negative 24x is just 0 here. F of xy, I get 24x minus 24y. The partial derivative with respect to y of this situation is just negative 24. And then I substituted back into my equation. So I get d is equal to 24.48y minus negative 24 squared, which gives us 1,152y minus 576. So the first point I decided to classify was 0, 0. So I plugged 0 into 1,152y minus 576, which gives us negative 576. Since d is less than 0 in this case, it means we have a saddle point. And then I calculated at 0.11. I did the same thing, which is just basically plugging back into our d equation. So I get negative 1,552 times 1 minus 576, which gives us 576. So we know that d is greater than 0. So now we have to look at what fxx is, which is 24. 24 is greater than 0, so we know we have a local minimum. And in this case, we don't have a local maximum.
Great. Very nice. So this is a perfect review for yesterday. Anyone has any questions? Okay, thank you, Cecilia. Yuri next, 3.47.
Yes, Professor. So here is the task. So the task says find the extrema of the function f of xy, which is equal to 3x plus 2y, subject to the constraint 2x squared plus 3y squared is equal to 3. So here we have the function f of xy and the constraint. So we decide to call it like g. So over what the first thing what I do is find the first partial derivative with respect to x and with respect to y of the function f of xy. If I had, let's assume, if I had function f of x, y, and z, then I would have to do another derivative fz, and so on and so on. So this is actually the result of it. So fx, which is the first partial derivative of x of f with respect to x, is equal to 3, and fy is equal to 2. So, and then the next thing what I do is just identify the constraint function, because here we have the equation and we have to identify what function we have so we can take the derivative of it. So in this case, I just move 3 to the left, and this is going to be my function g. And again, I have to find the partial derivatives with respect to x and y of this function, which describes the constraint. And the result of it is gx is equal to 4x and gy is equal to 6y. What we do next to find the extrema, we use the Lagrange multiplier method. So this method implies finding like another constant, another like multiplier, lambda, which helps us, which will help us identify the extrema of the function. And it's just the formula that fx minus this multiplier times gx is equal to 0, fy minus lambda gy is equal to 0.
Okay, hold on 1 second. Yuri,
Yeah.
hold on 1 second. Let me try to explain a little bit, because I haven't talked about Lagrange multiplier yet, but we're going to talk about it today. So Lagrange multiplier basically saying, you see here, Yuri has two objects, right? One is f of xy equals 3x plus 2y. And on the other hand, he has 2x squared plus 3y squared equals to 3. So we look at those two. The first one is a function. The second one, what is it?
It's
a level set.
Oh.
It's a constraint. But to us, the object is a level set. So out of a level set, we know we can make a function. That's why Yuri made a function g. So function g of xy, he made a 2x squared plus 3y squared minus 3. The constant doesn't really matter because equal to 3 equal to 0. We know this is a one level set. And also when we take partial derivatives, the constant becomes 0. So we could make a g of xy equals 2x squared plus 3y squared. That's fine. And you made 2x squared plus 3y squared minus 3. That's fine. And see, these two objects somehow subject to the constraint means these two objects intersect. So those two objects, those two functions, so function f and function g has intersection. One constraint to the other means they have something in common. Okay, what do they have in common? We call the constraint domain. Okay, we can understand that much because those two objects, in a picture-wise, you can think about two pictures, right, in your head, and these two pictures have an overlapping part. So on this overlapping part or on this common domain, they have something special. So they have a very strong relationship. What's the strong relationship? It's the gradient of one. It's gradient function, gradient of f equals to gradient of g with a scalar multiplier, with a scalar. Think about it like gradient of f equals to half of gradient g, or equals to 3 of gradient g. So that's the strong relationship between those two, because these two objects, those two functions, have a common domain. All right, so that's why Yuri here is using f partial x equals to lambda partial g partial x. So lambda is the letter we use to represent the Lagrange multiplier. All right. Okay, Yuri, go ahead.
Yeah, thank you, Professor. So, and then if we had the function f depended on z, we would have another fz, but here we don't have it. I just tried to do it and then recall that I don't have z. And the last function in the system of equation is our constraint in the form of the level set that we had. And then we solve the system of equation because we want to find first lambda, this multiplier, and then we want to find x's and y's, which give us critical points. So just substituting the functions, I got the result over here. And then from the first equation, I got that x is equal to 3 over 4 lambda. And from the second equation, y is equal to 1 over 3 lambda. And the constraint is, for now, I just leave it, and then I will use it a little bit later. So what I do next, oh, it's actually here. So what I do next, I just plug in x and y's in the formula for constraint. So it's like 2x squared plus 3y squared is equal to 3. But for now, x is equal to 3 over 4 lambda, and y is equal to 1 over 3 lambda. And I just saw this is just algebra. I solved the equation and get two values of lambda, which solve this equation. So at the end, I got positive and negative radical 35 over 72. So these are my two lambdas. And then I get back to these two equations over here. Now I know the value of lambda, actually two values of lambdas, and I substitute them into these two equations to find x's and y's. So it's just, again, just algebra, just simple substitution. So the result for x is positive or negative 9 over square root of 70, and y is positive or negative 4 over square root of 70. So combining these two results, these x's and y's over here, I got two critical points. The first one is positive 9 over square root of 70, comma 4 over radical 70, and the second is the same numbers but negative values. I think it's noteworthy to notice that I don't have the mix of them. Like I don't have negative 9 over square root of 70 and positive 4 over square root of 70, because we can see that if we mix them, we don't get the correct, like they don't combine to get the set of solutions for x's and y's. That's why I don't have the mixed positive and negative numbers for x's and y's. So now I have only two critical points. And to figure out if they are maximum or minimum values, I just plug in the numbers into the function f, like original function f over here, because now I know x's and y's. So at this point, the result is 30 over radical 70. And for another critical point, the result is negative 30 over square root of 70. And then I just compare these two numbers, and whichever is greater, it's a maximum value, and whichever is lower is a minimum value. And I conclude that we have maximum value of the function, which is 30 over square root of 70 at the point 9 over square root of 70, comma 4 over square root of 70, and minimum value equal to negative 30 over square root of 70 at the point negative 9 over square root of 70, comma negative 4 square root of 70. And that's it.
All right. Okay. Anyone has any question? All right. Very nice. Thank you. Dayeli, next one, then Ryan, then Tanya. Next one, then Ryan, then Tanya. Israel, Liz, Gabriel.
All right. I'm gonna present my screen. Also, if I make any mistakes, just bear with me. I literally had to learn this like last night. Okay. In section 3.3, we learned about maximas and minimas, and question 9 is asking us to consider our three given critical points, which are given here. Does everybody see my screen?
Yes.
All right. Okay. Cool. Okay. So then, we are given a function of x comma y, which is cosine x squared plus y squared, and they're letting us know that to consider this 3 critical points, but at the same time determine if we have a local minima, maxima, or a settle point. So I started by finding the partial derivative with respect to x of our function, and then I ended up with negative x times sine times x squared plus y squared. And now I did the same thing for the partial derivative with respect to y, and I ended up with negative 2y times sine times x squared plus y squared. And then I did the derivative with respect to xx, and I ended up with negative 2 times sine times x
Hold on one
squared
second.
plus, yep.
Hold on one second. Hold on one second. So let me see. I cannot mark this.
Yep.
There's no partial f over partial xx. All right. You can.
Yeah.
It's a partial square f. The second derivative. Partial square f over partial x.
Okay, so I'm missing the 2 for the
Square.
f square, right?
Right. It's partial
Yeah. Okay.
square f.
Okay. Partial square f. Got it.
Yeah. Partial
All right.
square f over partial x.
All right. Yes. Thank you. And then the same thing, partial of f, the partial of y times the partial of y, and I ended up with negative 2 times sine times x squared plus y squared minus 4y squared cosine of x squared plus y squared. And then I did the partial derivative of mixed partials, and I ended up with negative 4 times y times x times y times cosine of x squared plus y squared. And now I'm gonna move on onto using our critical point when is 0, 0. So our f would be cosine of, I'm just substituting my x and y here for the function of f, and then I ended up with positive 1, and I'm just doing the same substitution into partials. And if we notice that all of our partials are equal to 0, so that means that our test technically fails. But if we look at the function of f, which is negative 1, I mean not negative 1, positive 1, it indicates that our critical point is 0, 0. I mean no, it indicates that it's a local maximum at 0, 0. And then I move on to when our critical points are negative, not negative,
Y is a local maximum.
5 or 2. And then I'm just getting into my partials.
Hello. Why?
Yes.
The origin
Yes.
is the local maximum. How did you conclude the origin 0,
Can you repeat
0?
that? You're
So you said the test failed. As d equals 0, we cannot make any conclusion. But because f of 0, 0 equals 1, 0, 0 is a local maximum. Why is that? Why the function value equals 1, you can conclude 0, 0 is a local maximum.
because is greater than 0, our function of
From where?
0, 0.
So from where it says if the function value is greater than 0, the point you're evaluating at is a local maximum. Which theorem tells you to make that conclusion?
You're cutting off, Professor. I don't know if. Do you mind typing it in the chat?
Yeah, why? So how? Okay, type in the chat.
How do you conclude that zero is a local mass? Okay, so I'm looking, so by theorem 4 on the textbook, it explains that if U is an open is the different x of naught is a local streamer, then df, which is the or dependent, which I didn't write here, df of x naught equals to 0. Wait, no, I'm not confident, so I don't want to say a wrong thing because I'm not really confident on what to say, Professor.
All right. Okay.
I
Go
don't
back
want
to your
to say
function.
why I concluded that. Just
Your conclusion is right, but you just don't have the right reason.
yes. I'm gonna go back to.
Go up. So look at your function. What is your function?
Is cosine of x squared plus y squared.
What
Right.
it is what's the value range? What's your codomain?
Is in a 2D space.
It doesn't matter. Just only think about cosine of an angle.
Hello.
Cosine.
Yes, cosine of the angle, and then yep.
What is the value range of? I'm just trying to help you to understand why. The conclusion is right, but you don't have the right reason. The right reason is very simple. So read in the chat. What's the value range of cosine of x squared plus y squared? What's the value range of cosine of any angle? Someone is answering for you. Liz is answering for you. Josephine is answering for you.
-1,1.
It's not -1,1. It's the range
Wait,
is
I'm not from.
Okay, guys, Liz, Josephine, you're trying to help, but try to be exact. Okay, it's a closed set from -1 to 1. So now, can you tell us the reason why f of 0, 0 is a local maximum?
Because it's a closed set of -1, 1.
Yeah, that's the possible, biggest value. So that's why you can conclude 0, 0 is a local maximum.
Gotcha.
All right, keep going.
Okay. Yes. Okay. Just give me 1 second. I need to post something. All right. So now we've reapplied the same substitution to when we're given the critical points of square root of pi over 2 to our functions, and I ended up with our partial of f squared over partial of xx being equal to 2 pi. Same thing for our partial square of over the partial of y with respect to y. It will be equal to 2 pi, and then the same thing for the partial derivative of f with the mixed partial, and then determinant And then for the determinant, I ended up with it being equal to 0. This part, the test fails. And then here, when we plug in a square root of pi over 2 to our function, bless you, is equal to -1. So that means we have a local minimum because it's less than 0. Hello?
You finished?
No, I'm just gonna, okay, so then we're gonna do is 0 comma the square root of pi. We apply the same techniques of plugging in, and then I ended up with 0, 4, and then 0. I took the determinant, ended up with 0. Once again, the test failed, and then I plugged in our critical points into my function. I ended up with it being -1. So we ended up with a local minimum at 0 comma square root of pi.
So now you can tell us the reason, right? Why you conclude. Even the test
Yes.
fails, you can still conclude it's local minimum. It's because of function analysis.
Function analysis, got it.
Yeah, because you just recognize, cosine of any angle, the value is going from -1 to 1. All right? Okay, thank you. Let's Yeli.
Yes.
Ryan
Yes.
next.
All right.
Okay, thank you.
Does
Yeli.
anyone?
Then Ryan, then Tanya, Israel, Liz, Gabriel.
So I did question 31 from section 3. And depending on how you look at it, this question could be either really easy or really difficult, especially if you don't know where to start. So the question asks us to write the number 120 as a sum of 3 numbers. So that's, in this case, I put X, Y, and Z. You can use ABC. You could use whatever you want. And it also would like the sum of the products taken 2 at a time to be a maximum. So that's X times Y, Y times Z, and X times Z. And it wants us to optimize that to basically find the largest possible value for it. So the first thing I did was I converted X plus Y plus Z equals 120. I basically solved for Z, and I figured if I plug in Z, I can basically reduce it to 2 variables, and it shouldn't make too much of a difference because I can solve for Z later. So that's what I did, and I got this function right here, and I basically just called that f of x, y. And in order to find the basically the maximum of this function, I basically need to find a critical point. So in order to do that, I took the partial derivative with respect to x and to y, and I had essentially a system of equations, which is right here. And in order to solve that system of equations, I took the first function and I solved for y. I then plugged that in to here, and I basically got x is equal to 40. I then plugged 40 into here, and I got y is equal to 40. Now, that basically means that we have really one critical point, and that's at 40 comma 40. And so simply by solving for the original function, by plugging in 40 for x and 40 for y, and solving for z, z must also be 40. And that means that the largest possible sum of three numbers, which also is the largest possible the largest possible numbers to create the largest possible sum is going to be 40, 40, 40. And if you add those up and multiply the way it wants you to, it's 4,800. So that is the largest number that you could form under these circumstances.
All right. So yeah, so today we're going to talk about Lagrange method. Then you may go back, use the Lagrange method to do this question also. All right, nice Ron. Tanya next. Thank you. 3.33. Then Israel, Liz, Gabriel. Tanya?
Can you say it? 1 second.
Maybe it's coming up.
You can see it?
Yes.
Okay. So the question's asking to find the critical points of the given function and to determine whether it's a local maxima, minima, or a saddle point. So the function f of xy is x squared plus y squared plus 2xy. So first I found the partial derivative in respect to x, and that's 2x plus 2y. And then the partial derivative in respect to y is 2y plus 2x. Then I set 2x plus 2y equal to 0, and I got x equals negative y. And this shows that the partial derivative in respect to x will be 0 when x equals negative y. And then I did the same thing for the 2y plus 2x equals to 0, and I got y equals negative x. So that's also showing the partial derivative in respect to y will be 0 when x equals negative x. Then I did the second partial derivative of x, and I got 2. And then the second partial derivative of y, I also got 2. And then I did the mixed partial of x in respect to y, and I got 2 for that. So then I did d is equal to the second partial derivative of x times the second partial derivative of y minus the mixed partial of x times by y. And I did 2 times 2 minus 2, and then I got d is equal to 2. So in order to tell if it's a local maximum or minimum, you have to look at the d and also the second partial derivative of x. So here d is greater than 0. So that shows so far that it could either be a local minimum or maximum, but since the second partial derivative of x is also greater than 0, then that shows that it's a local minimum.
Okay, great. Let me ask you just one question. So, yeah, can you explain this part? Why do you set them to be 0?
Because the gradient f has to equal to 0, and then that's how you know that that's the critical point. So here the critical points are on the line y equals negative x and x like that.
Okay, that's right. That's the first derivative test. Okay, good. Thank you. Thank you, Tanya. Okay, Israel next. Israel?
Yeah, sorry, I was just getting my headphones on. Apologies. Okay, so for 4.11, it asks us to confirm whether or not the following equations are regular path. I will talk about that, but I thought this was also a good review for chapter 2 because it does discuss about tangent vectors a little bit. So basically what a regular path is defined as is just whenever we take the tangent vector of, let's say, c of t, if at any point along the derivative of c of t, t is not equal, it's never equal to 0, or the null vector, it is a regular path. So basically, mathematically, we can find that out for A, where we do c of t, where it's equal to cosine t, sine t, and t. You just take the derivative as just negative sine t, cosine t at 1. Obviously, because we have a constant, it will never change. Thus, it cannot equal the null vector. But also, I do have the graph here just to show you how it looked like. So as you see, like it's the tangent vector is a circle, whereas the regular vector is a coil going upwards. You see, in general, it stays around z of 1, and it usually never equals 0. Now, sorry.
Nice.
For B, we have where c of t equals t to the third. Sorry, t to the 3 squared. Sorry, I'm just very t to the third, t to the fifth, and cosine t. Once we take the derivative of that, that is 3t squared, 5t, negative sine t. Now mathematically, we can obviously see that it can equal the null vector because of the fact that when t equals 0, all the components will be equal to 0. So it is not a regular path. I also have it here as a graph to show you. Let me turn off the tangent vector real quick. Oops, sorry, that's what I needed. So here we have the regular vector, c of t. As you can see, it kind of crimps all here at c equals 1.
This kind of point has a name called a cusp. C-U-S-P. Yeah, cusp.
Yeah, a cusp.
Because at this point, you could see it's non-differentiable. It's a cusp.
Mm-hmm. So yeah, at the cusp, you can see it's non-differentiable, and once we turn on the tangent vector, you can see here. I'm trying. Let me zoom in so it's easier to see a little. Right here, at 0, 0, basically, you can see that it's basically. Oh well, again, I don't know what to call this. I kind of just call it a little crimp, like where you pinch something, like a piece of paper, it kind of crimps up.
Okay.
Creating that. Now for C, let me go a little over. We get the vector t squared e to the power of t and 3t plus 1. So again, like A, because we also get a constant, this cannot equal the null vector. But just to make sure, we also plug in t of 0 because we do have a variable t to see if we get the null vector. As you can see, 0, 1, 3 is what we get, as well as the fact that the reassurance that e to the power of t cannot equal 0 if t is any variable. I also have this the graph too to show you. This one isn't as exciting, but you see it's like two curves basically in a 3D space. That'll be it.
Very nice. Thank you. Liz, 3.37.
Yes.
Then Gabrielle, last 3.341.
The picture is loading.
Okay.
Can you see it now?
It's coming up.
Okay.
Yes.
For this question, we need to find if the critical points are local maximum, local minimum, or saddle points. So we're gonna start by looking for the critical points by finding the first derivative, and then we're gonna look for the second derivative to see if they are local max, local mean, or saddle points. So the function is f of xy equals to 3x squared plus 2xy plus 2x plus y squared plus y plus 4. So to find the critical points of the given function at a point x0, derivative of x at x0 must be equal to 0. So we're going to find the first partial derivative of the given function with respect to x and y. So partial f over partial x is the partial derivative of the function with respect to x. When we do that, that's give us 6x plus 2y plus 2. And next we look for the partial derivative of x with respect to y, and that's give us 2x plus 2y plus 1. Now we're gonna have each of them equals to 0. Partial f over partial x is 6x plus 2y plus 2, and we put this equals to 0. Partial f over partial y equals to 2x plus 2y plus 1 equals to 0. Now we're gonna try to solve for x and y. So I make my first equation equal to my second, and when I solve, I got value for x, which is negative 1 over 4. Then I substitute the x value into my second equation to find my y value, and my y value is also negative 1 over 4. Therefore, the critical point of this function, f of xy equals to 3x squared plus 2xy plus y squared plus y plus 4, is at negative 1 over 4 comma negative 1 over 4. So a point x0, y0 is local mean or max of f of xy if they satisfy those three conditions. Partial derivative of f over partial derivative of x at this particular point should be equals to 0. Second partial derivative of x with respect to x of this point need to be greater than 0 or less than 0. And third, we need to have second partial derivative with respect to x times second partial derivative with respect to y minus second partial derivative with respect to x and y at this particular point. If those three conditions are not met, we say that the point is a saddle point. So now we're gonna see whether the point is local maximum, minimum, or saddle points. So I start by replacing my point into my first partial derivative, partial f over partial x, and I replace x by its value and y by its value into the equation. Remember, it was 6x plus 2y plus 2, and this gives me 0. And I do the same thing. I plug in the point I found into partial f over partial y, and this also gives me 0. That means the first condition is met. Now we're gonna check for the second condition. I look for second partial derivative, which is just partial derivative of the first partial derivative that I found, and the second partial derivative with respect to x gives me 6, and the one with respect to y give me 2. The one with respect to x and y give me 2. So now I'm gonna replace x and y into the second partial derivative. At negative 1 over 4 for x, negative 1 over 4 for y. My second partial derivative with respect to x give me 6. The one with respect to y give me 2. The one with respect to x and y give me 2. So the answers didn't change because I didn't have any variables in my answers for the second partial derivative. So what I found will stay the same. I realized that the second partial derivative with respect to x equal to 6, which is greater than 0. So if the third condition is met, I will know that I have local minimum. So the second condition is met. We're gonna check for the last one, which is second partial derivative over with respect to x, times second partial derivative with respect to y minus second derivative with respect to x and y. Now we replace each of them by their value. So we have d equals to 6 for second partial derivative of x with respect to y times 2, which is second partial derivative with respect to y, minus 2 square, which is partial derivative of x over partial derivative of x, partial derivative of y square. So 6 times 2 give us 12 minus 4 give us 8. This is greater than 0, as d is positive and second partial derivative with respect to x is positive. By the second derivative test, the point -1/4, negative 1/4 is a local minimum of the function f of xy equals 3x squared plus 2xy plus 2x plus y squared plus y plus 4.
Great. Great. Perfecto. Thank you, Liz. Okay, Gabrielle, last one. Unless someone else like to present.
Okay, so I did number 41 of section 3 of chapter 3, and it's basically asking us to find the absolute maximum and absolute minimum values for a rectangle given this function, and then it closed it off at 0 did that whole thing, less than or equal to x or y and less than or equal to 2 pi. So the first thing I did was basically find the partial derivative at x, and then I evaluated it at equal to 0, and that, oh, sorry, wait. Let me preface this by saying I used 3 theorems. Theorem 4, which is the first derivative test, Theorem 6, which is the one that's like on the screen, it's the second derivative test, and Theorem 7, which is basically that if it's like a closed I think space or something. Sorry, I don't have it in front of me. But if it's closed, then there is an absolute minimum and maximum. And since it's a rectangle, it is closed. So going back, I did the first derivative test on the partial derivative of x, and then I got pi over 2 and 3 pi over 2, and that fit within the unit circle, and I'm not the best at that, so I included a photo here on the right, but you could just put in your calculator. And then I also did the same thing. I found the partial derivative at y, and then I just evaluated it at 0, so then I just looked for values of negative sine y that made the equation 0, and I came out with 3, which is 0, pi, and 2y, and again, it's all included within the boundaries that were given. So then I just paired them off, x with a y, x with a y, and I got 6 critical points. And then I, side note, and I did the fxx derivative, so the x derivative, the partial derivative of x from the first one. Sorry, that's a mouthful. And I did that for y too, and then I also did that for f sub xy. And then I got all that, and then I found the discriminant, which is also given in theorem 6 on the right. I basically just substituted, and I got sine x cosine y, and then I evaluated all 6 of my critical points, and whenever d was less than 0, it was a saddle point, so it wasn't included in my final answer. But whenever it was greater than 0, I either labeled it as a local maximum or local minimum based on whether fxx was less than or greater than 0.
And then after that, to find the absolute maximum, you basically just take your local maximum points and you put it into your very original equation in the beginning, and then both of them were this like both equated to 2, so that was my absolute maximum, which makes sense because it's like supposed to be like the greater of the two. And then the absolute minimum, I just did that for my local minimum and I got -2, which makes sense because it's the minimum part. So yeah.
Great, so neat. Okay, thank you.
Thank you.
Thank you. Anyone else like to present today? Okay. So we're going to talk about constrained extrema and Lagrange multiplier. Junyi, what do you mean before start the class? You want me to talk about question 3.2, question 1? Oh, okay, let's go to see that. 3.2, question 1. Yeah, do ask questions because you're in the review mood, getting ready for exam. So this is the 3.2. Let me just make sure. Yes, Taylor's theorem. 3.21. The first one, let f of x comma z equals to e to the x plus y. Oh, you know what? I think that's a typo. I think z is a typo. It should be f of x comma y equals to e to the x plus y. Maybe that's your question, right? Yeah, then the rest is easy. First order Taylor formula to approximate at 0, 0. Second order. Yeah, so it's x, y. So things like this, you know, this is obvious. X comma z, z is a typo. E to the x plus y. Because you see the points given are 2 dimensions, right? 2 dimensions. So this has to be y. Okay. All right. Okay, so we're going to talk about Lagrange multiplier today. Gabrielle, what's your question? Oh, do we read f sub xx? Okay, partial f, so second partial in x direction. So this one you can read f sub xx, you can read as a second partial in x direction. The second one, second partial in y direction. Then sub f sub xy, you could see second mixed partials in xy direction. Or you may read as a partial square f, partial x, partial y. All right, so this is short notation. We don't read fxx, no. Partial square f, partial x, partial x. You know, when mathematics is easy, but so many people, you know, were caught up with mathematics, thinking mathematics are difficult. Not at all. Because mathematics is just such honest subject. You know, if you try to be honest with the definition, with the theorem, you will never go wrong. But if sometimes you want to take a shortcut, you don't read the simple right. Because if we don't read the simple right, we are training our brain, not doing right things. If we're doing things right, if we're, you know, just follow exactly what it is, we are training our brain to be logic, because mathematics is just a string of logical ideas. All right, okay. But during your presentation, I just, don't have enough time to keep correcting people who are presenting, reading the wrong symbols. But ideally, even we use a shorthand notation, but still read it in a correct way. Thank you, Gabriel, for the question. Okay, constraint extrema and the Lagrange multiplier. Okay, what does mean constraint? Look at this picture, right? So we have this cylinder. Then somehow intersect with this surface. You see, these two objects intersect, right? Intersect at some points. So the intersection points are their common domain. Because they're sharing this common domain, or because they're intersecting at those points, so the behavior of these two functions are closely related. So another way we can think, okay, you see this cylinder is constrained by this surface at those points. All right, so that's how we understand constrained extrema. So constrained extrema means the extremas on those common domain of those two objects. All right, Lagrange multiplier. Okay, that's a famous mathematician, French mathematician. His last name is Lagrange. Okay, make sure we read this right to show our respect to those great mathematicians. Lagrange multiplier. Why is it called a multiplier? We use a simple lambda to represent because it's a scalar. So gradient of one function equals to a multiplier or scalar lambda multiplied by gradient of the other function. Or we may have 3 objects intersect, right? We may have 4. We may have n objects intersect. So which means one object could have n constraints. Okay, theorem. The method of Lagrange multiplier. So f goes from n space to 1 space, a real value function. G goes from n space to 1 space, a real value function. So you see, those two objects have to survive in the same domain and the same codomain. So at least first level differentiable, and let x naught an n space vector. So g of x naught equals c. So the constraint one usually represented as a level set, right? G evaluate at x naught equals c. We know this is a level set of that object. So S be the level set for G with value c. All right. And of course, we don't want to deal with gradient equals 0. Right? If the gradient equals 0, it doesn't give us any information. Because what is the geometric meaning of gradient? Gradient vector points the fastest way the function increases. Right? If it's 0, doesn't tell us any information. It doesn't move, right? There's no rate of change. It doesn't run. Okay, F restricted with, so this long bar, F vertical bar, S. Usually we read this S, we can read this S, or we read it as F restricted to S. F restricted to S. Has a local max or minimum on S, right? On S, because this S is now a temporary domain of F, or is a restricted domain of F. Then there's a real number lambda we call Lagrange multiplier, such that gradient F evaluate at the point equals to lambda multiplied by gradient of G evaluated at the same point or vector. And also we call the point x naught critical point of F restricted with S. Okay. Normally it's not a critical point for F, but it's a critical point for F on the restricted domain. Let's see this one. If F, when constrained to a surface S, has maximum or minimum at x naught, then gradient F of x naught is perpendicular or orthogonal to the surface S at the given point. The picture is this. Right? The picture is this. Gradient F evaluate at this point equals to gradient. Well, this is a similar notation, right? So because it's surface S, right? And the gradient F points to the fastest way of the function growing, and also it makes 90 degree with its tangent plane. Okay, this lambda we call Lagrange multiplier. This lambda, this is called lambda. So basically, we're using this equation. This looks like a one equation, but how many equations are hiding? If x naught is an n space vector, that means we have n equations, right? Depends on the dimension of the domain. Because partial f x naught, if the domain is n space, we would have a partial f, partial x1, partial f, partial x2, up to partial f, partial xn. So we have n equations, plus the constraint itself, the level set. So we have n plus 1. So this is n plus 1. So system of n plus 1 equations. So we're solving system of n plus 1 equations. Well, there are different ways to solve, right? Usually we try to find a smarter way to solve system of equations. Let's see an example. So the surface is given, and the level set is given a line through the point -1, 0, inclined at 45 degrees. Look at the picture. The picture is this. This is S. Right? It's a line passing the point -1, 0, and it forms 45 degrees with the x-axis. And we know the slope is 1, right? Tangent 45 is 1. The slope of S is tangent 45, which is 1. And we can write the equation for the level set. Right? Y equals to x plus 1. Because we know slope is 1, we are given this point, we can use the slope point formula to write the line equation and simplify it to be this. So this is a level set. And then out of this level set, we can manufacture function g. The g of x comma y equals y minus x minus 1. Because when we take a partial derivatives, this constant -1 doesn't contribute because it becomes 0. So this constant part doesn't really matter. you could see, okay, I want a g of x1 equals to y minus x. That's totally fine. Then function f is defined as x squared plus y squared. So what do we want to do? We want to find the extrema of f restricted to s. All right, we find the gradient f, gradient g, or gradient g is 1, -1, 1. No, Zaman, I'm Mohammed. We already finished presentation. You present the next class. I already asked, all right? Yeah, it's too late. I'm already teaching. Present next class. Okay, we still have enough time. So gradient G is -1, 1. Then we calculate the gradient F. Well, gradient F is just 2x, 2y. Right now we have a system of 3 equations. Right, if you want, you can list partial f, partial x, which is 2x, equals to lambda multiplied by partial g, partial x, which is -1. Okay. Then partial f, partial y is 2y equals to lambda multiplied by partial g, partial y, which is 1. So 2x equals to -1, 2y equals to 1. You have this system of 2 equations. That gives you x equals -1, or y equals to -x. Then you're working with this constraint, working with this. So you substitute x equals to -y or y equals to -x into this. So what do we get? -x equals to y, so we have y plus y equals to 1. So y equals to half. Then because x equals to -y, so we get x equals to -half. So we did find a critical point of f restricted to s, which is -half, half. Right? And this says it's a relative minimum of f with restricted to s. And f on s has a minimum, relative, or local minimum, but no maximum, because we only have one critical point of f restricted to s. Why is a local minimum of f restricted to s? You can go back to the function, right? Or you can use a second derivative test. What is the -I, -j, -i, j? You forgot? That's -1, 1. I equals to, I is a vector, is 1, 0 into space. J is a vector, equals to 0, 1. Okay, cannot forget the vector notations. Okay, let's see example 2. So this one, f is defined as x squared minus y squared. Okay, so S is a circle of radius 1, unit circle radius 1 around the origin. So which is what? X squared plus y squared equals to 1. And we want to find extrema of f restricted to s. So s is a level curve for g. So what is a g? G can be defined as x squared plus y squared, right? Because x squared plus y squared equals 1. It's a level set. So out of the level set, we manufacture a function g. You can define g as x squared plus y squared minus 1. or simply just forget about the constant. Because when we take a partial, when we take a gradient of g, the constant becomes 0. So we use the Lagrange multiplier, right? Then we find the gradient f, find the gradient g. Then we set as a system of equations. And with the constraint x squared plus y squared equals 1, so we have system of 3 equations, right? Then we solve, we get 0 plus 1, 0, 1, and 0, negative 1 to be the and 1, 0, negative 1, 0 to be the critical point of f restricted to s. Then we can use the second derivative test to classify those critical points, right? Gradient f is 2x negative 2y, gradient g is 2x 2y. Well, 2x equals 2x, negative 2y equals 2y. That tells you y has to be 0. Then you plug in x squared plus y squared equals 1 because y equals 0. So your x can be positive, negative 1. Right, the picture is this. The picture is this. Right, 2x equals to lambda 2x, so lambda equals to 1. Negative 2y equals to lambda times 2y, so lambda equals to negative 1. Right. So for this equation, either x is 0 or lambda is 1. Right? If x is not 0, that means lambda equals 1. Then we substitute into this equation, we get a y equals plus minus 1. Right? If x is 0, we get a y equals plus minus 1. Or the second equation of negative 2y equals lambda 2y. That means lambda equals negative 1 or y equals 0. But if y equals 0, we plug into this equation, we get x equals plus minus 1. Anyone has any question? Solving system of equations. Form system of equations. Solve system of equations. Okay, let's see this one. Maximize this function, x plus z, subject to this constraint. So we form a g function, right? G function could be x squared plus y squared plus z squared. Then partial f is 1, 0, 1. So partial g, partial x, 2x. So 1 equals to 2x lambda. Partial f, partial y is 0. Partial g, partial y, 2y. So we have 0 equals 2y lambda. Then partial f, partial z is 1. Partial g, partial z, 2z. So 1 equals 2z lambda. So I have 1, 2, 3, 4. 3 equations from a Lagrange multiplier method. Then we have this constraint. So we have a system of 4 equations. So we have to solve this system of 4 equations. Well, lambda cannot be 0. Okay, lambda can be positive, can be negative, it will never be 0. So that means forces y to be 0. So forces y to be 0 here. Now here we have 2x lambda equals 1, 2z lambda equals 1. So 2x lambda equals 2z lambda. That forces x to be equal to z. Right? Then we substitute into this. Y equals 0, x equals z, or z equals to x. So I have 2x squared equals to 1. That means x squared equals to half. Well, with square root. So x equals to square root, positive, negative, square root of half. Right? Or just 1 over square root 2. So we have 1 and 2 critical points, because x can be positive, can be negative, and z equals to x. So we have, if x is positive, z is positive. If x is negative, z is negative. So I have these 2 critical points. Then we can compare the values of f at those points. All right. Then we can conclude the biggest one indicates the points, maximum point. The lowest value is local minimum. Okay, anyone has any question? So this is a function with one constraint. A function can have n constraints, but for this class, we're only going up to 2. Okay, Lagrange multiplier is such important concept, and it's very easy to apply for any science major, even for economics major, all right? Let's see this one. Okay, this is one application. Assume among all rectangular boxes with a fixed surface area of 10 square meters. So the constraint is the surface of this rectangular box is 10 square meters. Right? So we have to remember how to calculate the surface area of a rectangular box. And there is a box of largest possible volume. All right. Find its dimension. Find its dimensions. That means we need to find the critical points. We need to form a function f, form a function g, then use Lagrange multiplier method to find critical points on those common domain of those 2 functions. All right, so we call the 3 dimensions x, y, z, right? And of course, they're non-negative. And the volume we can set up as a function f, right? Just multiply 3 dimensions, x, y, z. And the constraint is the surface area because it is given 10 square meters. So we know this is a constraint. So 2xy plus 2xz plus 2yz equals 10. Simplified to be xy plus xz plus yz equals 5. So we form g function. G function is xy plus xz plus yz. Right? Then Lagrange multiplier method, gradient f, right? Partial f, partial x, yz, partial f, partial y, xz, partial f, partial z, xy. Partial g, partial x, y plus z. Partial g, partial y, x plus z. Partial g, partial z, x plus y. Then multiply by Lagrange multiplier, which is a lambda. Then we have this constraint. So we have formed a system of 4 equations with 4 variables. So 4 equations, 4 variables, guaranteed, solvable. Okay, the first one, so personally, how would I solve this? I would multiply x on the both sides of the first equation to make x, y, z on the left-hand side. I multiply y for the second equation to make x, y, z on the left-hand side. I would multiply by z on the third equation to make x, y, z on the left-hand side. Then I can get rid of this x, y, z's, right? I can have lambda x, y plus z equals to this, multiplied by y equals to this, multiplied by z. Then I work with this, right? Then I work with this. In any case, you may have different method to solve this system of 4 equations. All right. So in the end, what do you get? You get x equals y equals z. It's a box. It's a square box. And the side equals square root of 5 divided by 3. So the maximum volume is just this one multiply itself 3 times. So we can write it as 5 over 3 raised by the power 3 over 2. Anyone has any question? Okay, so those are functions with one constraint, and then typically this one is application. We may have multiple constraints. So we may have several constraints, right? So what do we do? And we would use number 1 for the first constraint, number 2 for the second constraint, so on and so forth. Okay. We use a number with a footnote. Let's see this example. Function f is x plus y plus z with 2 constraints. The first one is a circle with radius of square root 2, x squared plus y squared equals 2. So we can manufacture g1 function. G1 function is x squared plus y squared. And the second constraint is x plus z equals 1. So we may make a second constraint, g2 function. G2 function equals x plus z, right? So gradient f is 1, 1, 1. Gradient g, the 2x, 2y, right? There's no z, so z just 0. And the gradient g1, gradient g1 to x to y, gradient g2 is 1, comma 0, 1. Right? Gradient g1, no, function g1, function g2, gradient f equals to number 1 times gradient g1. Plus, this is a plus, okay? Because if you think of it, the rate of change of f on the restricted domain equals to certain Lagrange multiplier multiplied by the gradient of g1 plus gradient of g2 plus multiplied by another Lagrange multiplier. So we form a system of 5 equations, right? So 3 comes from the 3 directions of the domain, and 2 comes from the constraints, right? So we have 5 variables and 5 equations guaranteed solvable. So you may use different ways to solve this, all right? So in the end, we get 0, square root 2, 1, and 0, negative square root 2, 1, to be the critical points of f on those 2 constraints. It says by inspection, all right? Just evaluate f value. Well, f equals to x plus y plus z, right? So of course, those positive ones gives maximum. And this with a negative 1, negative square root 2, positive 1 gives local minimum. Okay, any questions for this? You see mathematics, right? If you have the proper prior knowledge and you build up on it, so the new concept is easy to accept or to understand because it's very logic, right? There's no imagination in it. We don't have to create. Well, creative is something else. Anyway, so yeah, that's for 2 constraints. Let's see this one. We want to find absolute max of f is defined as x times y on the unit disk. Well, remember, unit disk is a close bounded set. It has interior points, it has boundary points. So the representation of this unit disk is this, x squared plus y squared less than or equal to 1. So one part is x squared plus y squared less than 1, open set, right? On the open set, we don't need to use Lagrange multiplier, right? We can use the first derivative test, the second derivative test to find critical points and to classify critical points. But on a closed set, we cannot apply first derivative test and second derivative test. So what do? We use a Lagrange multiplier. Right. So this is a combination of first derivative test, second derivative test, and Lagrange multiplier. Because we're dealing with open set, x squared plus y squared less than 1, we're dealing with a closed set, x squared plus y squared equals to 1. All right, we're dealing with the first open set. Open set, we use first derivative and the second derivative test. Partial alpha partial x equals to y, partial alpha partial y equals to x, set to be 0. That means the origin is the only critical point for f on this open set. Then we can use the second derivative test to see if it's a local minimum or local maximum, or we observe the function. Okay. We cannot do mathematical analysis because x can be negative, y can be negative, and here we have 0, right? So we cannot use analysis to conclude if it's maximum or minimum. Or we can wait for when we find all critical points. Then we evaluate the function value, then we compare. We can wait, okay. So we find 0, 0, the origin is a critical point on the open set by first derivative test. Then we use the Lagrange multiplier to find the critical points on x squared plus y squared equals to 1. We're treating x squared plus y squared equals to 1 as a constraint of function f. So we form G as x squared plus y squared. Then we use the Lagrange multiplier. Then we form a system of equations. Then we solve. Right? So get 4 critical points. Then we can calculate the function value at this 4 plus this one, right? So this one is a critical point on the open set. These 4 are critical points of f restricted to G. Then we'll compare the values. So the absolute maximum is f equals to half. Whoever is given, so those 2 points are given function value to be half. So those 2 points are absolute maximum. And those 2 points give negative half. So, and the 0, 0 gives 0 is in the middle of negative half and a half. So those 2 points gives absolute minimum. Or you can use second derivative test for 0, 0. All right. And if you use that, that tells you it's a saddle point. It's neither max nor minimum. Anyone has any question for this? All right. Let's see this one. Function is defined as this: half x squared plus half y squared. Constraint, or this close bounded set is given as this: half x squared plus y squared less than or equal to 1, same as example 6. Okay, we separate this closed and bounded set into 2 parts. Into open set, we're using first derivative and second derivative test. And for the closed set, we use Lagrange multiplier. All right, so same way. Global max minimum. So boundary, we said the boundary is smooth. If boundary is a level set of smooth function with gradient, okay, it's not so important for us. Okay, let's see this. Lagrange multiplier strategy for finding absolute extrema with boundary, which we showed, right? So f is differentiable function on the closed and bounded, okay, closed and bounded region D, which means D has open set part and has a boundary part. And smooth means the function is differentiable, all right? Smooth. There's no cusp, no corner. So function is differentiable at all points. Smooth, that's what smooth means. So locate all critical points of f in the open set, which we see from the previous examples, right? First derivative test on open set. Use Lagrange multiplier to find the critical points of f on the boundary. Because boundary is a closed set, we can only use the Lagrange multiplier method. Then compute the value of f at all critical points. Then compare them. The largest is the absolute max. The smallest is absolute minimum. Let's see one more example. F is defined so, and D is this closed and bounded set. Open set part is less than 1. Constraint part is equals to 1, the boundary. Open set, we use first derivative test. Boundary, we use the Lagrange method. Right? Then we form a system of equations. Then we solve. Then we compare all the values, function values at all the critical points. Okay, anyone has any questions? Okay, if not, that's all I want to talk about this section. This section is a Lagrange multiplier, all right? Lagrange multiplier, why we need it? Because the first derivative test only used for open set. So we need a Lagrange multiplier method to look at it from another point of view. Okay, if you have no questions, you are free bird for today. Go ahead, start your homework. If you have any questions, I'm still here to answer your questions. All right?
Professor?
Yes.
So for last week, did you input the grades yet for the presentations?
Yes, I did. Yes, I did.
Last week I presented, but you didn't increase my grade.
I didn't?
Yeah, I presented last Thursday, 3.1.9.
Yes, you did. I did. I did give everyone credits. I didn't give to you.
Yeah, because, yeah, I didn't get 10 points.
Hold on one second.
Because it says the last time you updated was the 25th, and I presented on the 27th.
Ivy presentation. Okay, let me check because I have all those here. I have the count.
Okay, thank you so much. If you need, I can send back I can resend the work for you to check, or I'll look back in the recording.
No, I have write down your name and number here. So I just have to count how many, because this shows you presented 4 times, but you are seeing you presented 5 times in total, right?
Yeah.
Okay. All right.
All right, thank you so much.
Check my notes.
Okay, have a nice day.
You too. Josephine, you can always present next time. Okay, we have enough classes for you to present. So present the next class. Ideally, tomorrow we present 3.4. All right. 3.3, if you have some interesting questions, yes, you may still present, but no more basic stuff. Okay. All right. Thank you. Thank you. Any other questions? Thank you. You too. Or let me